Section 11.1, and we are now going to start our last chapter, and this is on limits. Here we go with the definition of a limit. If f of x, right here, arbitrarily becomes arbitrarily close to a unique number L, as x approaches c from either side, the limit of f of x as x approaches c is L. So here's what this says. If we have a function and we substitute numbers into the function and the numbers that we substitute slowly approach this number c, whatever c is, from either side. So it slowly approaches it from the left side, thinking of like a number line, and it slowly approaches it from the right side. So what we've got is we just have a number line and c is some number on the number line. Then as the limit, as x approaches c, within this function here, the result of the limit is equal to L. There will be a couple of scenarios or examples that we actually find this information so that you can maybe see a better representation of this definition. In this first example here, we want to do the limit in two different ways. One way will be to algebraically substitute numbers in or use our table feature on our calculator where we set up the scale. And then another would be looking at the graph. So let's first look at the calculator. So you're going to want to do this in Y1. You're going to want to enter this function here. Go ahead and enter that into Y1. You're going to want to use and set up your table feature. If you go to your table feature on your graphing calculator, I would recommend starting your table at negative 2.5 and then going by a scale of 0.1. So this is for your table setup. And then in order for us to see what the function does as we evaluate for x values, we're going to substitute what the table is giving us here into my chart on this page. So going to the table now, at negative 2.3, the result is negative 0.3. At negative 2.2, it's negative 0.2. And at negative 2.1, it's negative 0.1. So what we would ask is, what is this slowly approaching? What number is this slowly going towards? And we want to look at it from the left side, so the negative values, and now again from the right side. Negative 1.7 is 0.3, and then it's 0.2, and then it's 0.1. So when we do limits, what the limit is asking is, what is this function approaching as the x approaches negative 2? Well, that's this number right here. So you can see from the left side, we're slowly getting closer to 0. And from the right side, we're slowly getting closer in this direction right here. What's it slowly approaching? What's it slowly approaching? And so the answer to this limit is 0. Okay, so algebraically, that's what we would do. Now, to find the limit graphically, you should have your function already in your calculator. So go ahead and push graph. Zoom 6 would be probably the best for us. And what we can see here is that our graph looks like this. So the question is, what is the graph? What's the result of by looking at the graph as it approaches negative 2? Well, this is my negative 2 value right here. This is when x is negative 2. So the y value, it's 0. So there's two different ways to look at your limit. You can look at it from a graph or by substituting values in. Again, it's what your function is slowly going towards or what it's approaching. We also have some other information here. The existence or non-existence of f of x when x equals c has no bearing on the existence of any of the following, or has no bearing on the existence of the limit of f of x as x approaches c. What we know is this. There's three cases here that we want to look at. The first one, go ahead and put these into your limits that fail to exist. So it does not exist in the following conditions. F of x approaches a different number from the right side, and then as it approaches from the left side. So on this example right here, we would have found different numbers coming from the left and from the right. So that's when the limit does not exist. So this is all does not exist. If f of x increases or decreases without a bound as x approaches c, and these are some things that we'll look at here in a little bit. And f of x would oscillate between two fixed values as x approaches c. When it says that it increases or decreases without bound, this is what that might look like. Maybe we have one graph slowly approaching positive infinity and the other graph here slowly approaching negative infinity. See, there, it's not consistent. When it oscillates between two fixed values, the oscillation, we might have a graph that does this. And so that shows that it's oscillating back and forth, and so there's no limit either. All right, we're going to take a look at just a few examples here that relate to the what we just had talked about, and we'll try to walk through finding the limit of each of these three examples. The second example, let's just think about values, like if we were building a table of values like this, you know, what would this graph look like? So let's say what if x was small, really small? Let's say -5. So -5 divided by -5 is positive 1. Or actually, when you take the absolute value of your -5, and here it's positive divided by a negative. So we're looking at when x is -5, then the y value is -1. And if it's -4, then it's -1, -3. So we basically, as we are approaching here 0, my answer is always -1 coming from this side. Now obviously it wouldn't be 0 here because then it would be undefined. You can't divide by 0. And when x is +1 or +2, 3, or 4, or 5, we always get a value of +1. So this is what our graph looks like. So from the left side here, as we are approaching, it shows that from the left side it's approaching 1, which is negative, but on the right side, coming this direction, it's approaching +1. So since they're not consistent here, there's no limit. All right, in the next example, let's go ahead again and look at some values and pretend like we're plotting points. We can't have x to be 0. In fact, we're trying to find what the limit is as x approaches 0, and since we can't divide by 0, this is why we're having problems with finding the limit. But if x was, let's go with positive x's, as x is 1, so as we increase our x here, the value gets smaller and smaller and smaller, like 1/4, 1/8, 1/16, 1/32. So my graph would actually come here and approach like this, slowly approach the axis. And if it was negative, I'm still squaring a negative, but if I have a negative value, I'm substituting in for x. I can go ahead and still get the same results as x is close to 0 here, and I slowly decrease the x value to a negative. It's slowly getting closer and closer and closer to 0. So we're looking for y values here as x increases here on the right side, the output is slowly going to positive infinity. And as x gets really small, it's slowly going to negative infinity. And so it's going to infinity here, and they're not consistent. So this is, again, no limit. And finally here, again, we can't divide by 0, so there's a problem with this limit. And what we want to look at is what happens with our values. So what this looks like here, and again, this is the sign of 1 over x. Now you can always graph these and kind of look at what the graph is going to be, but it makes it just probably as easy to do some substituting of some points. Since we are graphing a sign, I recommend changing to radians so that it'll read some things. But what happens is this graph kind of comes in here and does this oscillating back and forth and then goes back out. So anytime that you see this, and you're probably going to have to use your graphing calculator here and substitute that into y1 and go ahead and graph it in radians. But because of that oscillation here, then this is also considered to be no limit. So this is when limits are not able to be found. We got 3 cases here. All right, the next thing we're going to look at is just, how do we do some evaluating on a limit? There are some properties. There are 4 properties here. You might want to pause the video and go ahead and write down these 4 properties along with the example that they go with. The first property is taking the limit of b as x approaches c. Well, basically what you do is you substitute c into the function. So the result, and since b here is a real number, so b is something like 10, then the limit would just be itself. Okay, here's our example. The limit as x approaches 2 of -5. Well, if I go to substitute in 2 in, there's no x's. So the result is just -5. I could do this, the limit as x approaches 0 of 3. So the answer is just 3. Okay, so that's always the case for finding the limit of. Here, if I try to substitute on the second one, I can actually put the c in for x and the output would be c. So it's kind of like evaluating functions. Here's an example here with 4. So if I put 4 in for x, then the output is 4. Now you can use powers, you can use roots. If I substitute c in here for x, then the output would be c to the n. Or, as x approaches 3, x squared approaches 9. That's how we refer that information. And for this nth root, as x approaches c, then I've got c underneath my nth root, so the nth root would equal, so the limit would also approach the nth root of c. And here we've got, so putting 3 in, the 4th root of 3. So that's kind of how you work with limits. We will look at a lot of different properties here, and you're going to want to pause the video, make sure you get the properties down, and you will be able to take a look at an example or two with them. All right, so let b and c be real numbers and let n be a positive integer. F and g will be functions with the following statements about operations with limits. So here's what we've got. If the limit as x approaches c of the function f of x is equal to L, so this is, if that's equal to L, and the limit as x approaches c of g of x is equal to k, so this is equal to k, then the following properties exist. A scalar multiplication. So if this is my function, and in my function I had this, there's a scalar that is being multiplied by the function, then I also have the scalar being multiplied by the result of the limit. An example would be if I have the limit as x approaches c of 3x, let's say, then the result is 3c. You can put the c in 3 times c. So that's kind of how this works. There's some or difference. So if you are adding the functions together, then the limit as the addition of functions would be the result, plus or minus. And product, if you're multiplying them together, again, the result of the limit would be also the multiplication of their answers. Let b and c be real numbers and let n be a positive integer. F and g are functions, and again we have the same case here. So the limit as x approaches c of the function f of x equals L. The limit as x approaches c of the function g of x equals k. So the quotient, a limit with the quotient here as x approaches c is L over k, another quotient, and an exponent. So this exponent rule also applies. As x approaches c of this function to the exponent, then the result is L, which is again the result of the function, to that same exponent of n. All right, we're going to go ahead and do just a couple examples that maybe help us with understanding some of these properties. This first one is example 4, and it says find the limit of as x approaches 4 of 3x squared. Well, again, if we're just algebraically finding the limit, we can just do 3 times x, which is 4, squared. So this is 3 times 16, which is 48. So my answer is 48 here. Again, we're not running into any problems because x is not approaching 0. It's when it approaches 0 that we have to look at what's going on with our function. If p is a polynomial function and c is a real number, then as x approaches c, again, just showing that we can just take this information and substitute. It equals p of c. If r is a rational function and c is a real number, then r of x equals p of x over q of x. Again, so we're showing some a quotient here, and again you would just substitute your c value in. We got one more question here to look at. Example 5, finding the limit as x approaches 2 of this function. So, again, we're going to just do 4 minus 2 squared over 2. 4 minus 4 over 2. So 0 divided by 2. So the answer is 0. So that's how you kind of evaluate some limits. Here's a just a brief assignment with to get an understanding of how to use the limit.